Hello everybody, my name is Marissa Loving and I'm an NSF postdoc at Georgia Tech. And today I'm going to tell you a bit about n-periodic homeomorphisms and volumes of mapping tori. As you can see on my slide, this is just part one of what will be sort of a two-part series on these topics. And this first talk is really going to focus on this first piece of the title, n-periodic homeomorphisms. So the outline of the talk is roughly as follows. I'm going to introduce surfaces of both finite and infinite type, and then I'm going to talk a little bit about the ways we can sort of go between surfaces and three manifolds, whether that's building a three manifold from a surface or just finding surfaces in three manifolds. And then we'll wrap up with a definition of n-periodic homeomorphisms. So what are surfaces? Well, surfaces are two-dimensional manifolds. I'm first going to introduce finite type surfaces. Okay, so I've drawn here a few examples. I've drawn a sphere. This is probably one of the most familiar to all of us. You can think of this like the surface of the Earth or the skin of an orange. There's a torus, a genus 1 surface, the sort of classic surface that we associate to topologists, right? It's the like joke about a donut or being the same as a coffee mug. And then here we have a genus 2 surface and a genus 3 surface. And here when I'm talking about genus, I'm really talking about these sort of central holes. So here's our genus on torus, and then this genus 2, and then we can see here the genus 3. Okay. And so the important thing to keep in mind is that when I'm referring to a finite type surface, I mean that my surfaces always have finite genus, like the ones I've shown, and finitely many punctures. Okay, so all of the surfaces I've drawn here are closed. They don't have any punctures. But we could consider sort of taking out a few points. For example, I could remove 4 points. Think of just sort of taking a pinprick out of my sphere. This gives me a 4-hole sphere. Or I could remove a couple points for the torus, a point from my genus 2 surface, for example. And one of the results that really makes it easier to study surfaces and to sort of describe the types of surfaces we're thinking about is this theorem called the classification of surfaces. So here you'll note my little asterisk. I'm talking about surfaces of finite type. And the classification theorem tells us that a connected orientable surface of finite type is determined up to homeomorphism by its genus and the number of punctures. Okay, so sort of another way of formulating this theorem is to say that if I sort of list out my surfaces, like I have down here, I have my sphere, my torus, my genus 2 surface, my genus 3 surface, and then we can sort of think of the genus increasing as we go out to the right. And then as we go down, you see I've added some mark points. So I added 1 here, I had 2 punctures here. And so you can think of the punctures increasing as we go down. Then this sort of list, right, this sort of table that I've enumerated, well, this is really all of them. This is all of my surfaces. Okay, so in order to describe, if I'm holding a surface and I want to describe to you what surface I have, I just need to tell you those 2 pieces of information. How much genus does it have? How many punctures? Okay, so this is pretty nifty. And one of the things that we study, and by we, I mean geometric group theorists and some low-dimensional topologists, in association with surfaces, is a group called the mapping class group. Okay. So the mapping class group is the group of orientation preserving homeomorphisms of my surface S, so of S, up to homotopy. Okay, so in particular, if I have 2 homeomorphisms and I can kind of wiggle them, kind of smoosh them along on the surface to look like each other, then I want to say that they're the same mapping class. Okay, they give rise to the same mapping class. And one of the ways that we're able to really sort of get our hands into understanding what the mapping class looks like and use it to give us information about our surface is the following theorem called the Nielsen-Thurston classification. So I've shown sort of the Nielsen-Thurston classification here in this sort of diagrammatic picture. Okay. And what the Nielsen-Thurston classification does, well, it classifies the types of elements that we see appearing in the mapping class group. And it says that really there's sort of these three flavors. There's elements that are called finite order. Okay, and this is sort of just our familiar notion of finite order from group theory, where if we have an element, we sort of raise it to some finite power, then we get the identity. Okay, we have elements which are reducible. Okay, so that means that there's some collection of curves on our surface that is preserved under the action of our mapping class. Okay, that collection of curves is called a reducing set. And then in this complementary region, there's these elements called pseudo-Nazev. And so I said here that pseudo-Nazevs are dynamically complicated, and they're sort of the most interesting flavor, I would say, at least for me. I won't speak for everyone. But so they're sort of one of the most interesting flavors of mapping classes that we have. And so pseudo-Nazevs actually sort of have a bit of a technical definition that I won't get into, but they have a really rich structure associated to them. And one of the outcomes of the Nielsen-Thurston classification is to say that this structure actually exactly coincides with being the elements of the mapping class group which are infinite order and irreducible. Okay. And I've given just a couple of examples down here for folks who aren't super familiar. I've given an example here of a finite order element of the mapping class group, which is just this rotation of this genus 3 surface, which I've drawn sort of like a fidget spinner here. So here I'm rotating by 2 pi over 3. And you can see that sort of if I apply this 3 times, I'm going to come back to sort of my original position. My fidget spinner sort of comes back exactly to where it started. And we also note that we sort of have these curves here, which are being preserved under the action of my rotation, right? They're all getting sent to each other. So none of them are fixed under the action of my mapping class, but they're sort of preserved as a set. Okay, so this sort of actually fits right here in this middle part, right? Because it's not only finite order, but it also has a collection of reducing curves. And then here, I've drawn another example. This is something called a Dane twist. So here's the actual homeomorphism, is if I take this sort of blue curve and I twist it around this red curve. Okay, so you can see the action on this curve. I come around, twist, and I go back. And so you can also sort of think of this homeomorphism as if you sort of cut open your surface along your red curve, you twisted it by 360 degrees, and then you glued it back together. Okay, so this is an example of something, again, that's reducing, right? Because this red curve is fixed, but it's actually infinite order. And so it sort of lives here in this part. And I actually haven't given any example of a finite order irreducible element, but that's fine. You can just take my word on it. Okay, so with this sort of classification in hand, let's move on now to talking a little bit about the infinite type setting. Okay, so surfaces now of infinite type. We have some pictures here. I sort of have the same type of description now for the infinite type setting as I did for the finite type setting. So in the finite type setting, we are always assuming that we had finite genus, finitely many punctures. In the infinite setting now, we are always having either infinite genus or infinitely many punctures, or we can have combinations of both. So let me just for a minute sort of take off these pink ones. Okay, and then we'll sort of come back to that in a second. So I have 3 surfaces drawn here. I have this Loch Ness Monster, where we sort of have infinite genus going off in one direction. I have this one called a Jacob's Ladder, where we have sort of genus going off in 2 directions. And then I sort of have this third one, this tripod, or as I'm trying to popularize, an Eiffel Tower, where we have this sort of genus going off in 3 directions. So I just want to point out that not every infinite type surface has a name. I really chose these ones specifically because there's some ones that we might deal with a little bit more often. And that's why they actually have those special names. But of course, these are all surfaces that have genus, but don't have any punctures. And so I can add back in what I had shown before, right? Where we could also have sort of punctures, right? We could have these sort of infinite isolated punctures also going off to the right here. We could remove some finite collection of punctures, like this. Or what I had drawn over here on the Eiffel Tower is we could remove like a whole big collection of punctures. So we could remove, this is sort of my very crude drawing of a Cantor set. So here we're moving not isolated punctures, but a whole Cantor set worth of punctures. Okay? So this is obviously, at least to me, feels like a lot more complicated than the finite type setting, right? There's sort of a lot more that could happen here. But it turns out that we still have a very nice classification theorem. So the classification theorem of infinite type surfaces, this is something that was given by Kerk-Jarto and then was sort of completed by Richards. And it says that a surface of infinite type is in fact determined up to homeomorphism by three things. So by its genus, just like before, except now the genus is either some finite number or it's infinite. And then these two other things that aren't just sort of numbers or parameters, they're actually spaces. So it's space of n's, and then the subspace of n's accumulated by genus. Okay. So I haven't said what I mean by n's, and I'm not going to give a precise definition, but I do want to give some notion of what I mean. Okay, so when I'm talking about these spaces of n's, I'm thinking of sort of how we can go to infinity, right? That's sort of what I was saying on that first slide with the Loch Ness Monster, with the ladder surface, with the tripod, where you can see that this genus is sort of going off, okay? So what do I mean by going to infinity? So let's consider the real plane and the real line. So if you're standing at the origin of the real plane and you're sort of looking out, in some sense it feels like you have a lot of different directions to go, right? You can sort of turn any way you want and you can sort of go off as far as you like. And so there might be some intuition that might say, well, there's sort of infinitely many ways to go off to infinity on the real plane. And I want to sort of challenge that a little bit by instead considering what happens when you sort of delete bigger and bigger pieces out of the middle of the plane. So for example, what happens if I remove this pink circle, right? We just sort of took a cookie cutter, cut it out of the plane, and we still have this sort of big single connected piece. Right, and we could take out a bigger chunk. Okay, so there I took a bigger cookie cutter, took it out. I still get a single connected piece in the complement. What happens if I take out an even bigger one? Right, well, it doesn't really matter how big of a chunk I take out. I'm still getting so that connected piece outside. And so even though in some sense it feels like we can go out in any direction to infinity, really we just are sort of going one way. Right, we're going out to that end. And in the same way, when we look at the real line, if we sort of take out bigger and bigger pieces, we're always decomposing into these sort of two directions, off to the positive infinity and off to negative infinity. And so we say that we have two ends here. Okay, so this is sort of my idea for how I want us to think intuitively of the ends of our surface. So how can we use this notion of ends then to actually tell apart our infinite type surfaces? Well, for example, we could consider sort of this picture. If this was happening live, if you folks were sort of actually talking to me right now, I would ask for the audience to tell me which, if any, of these surfaces are the same, right? Which of these images that I've drawn are actually homeomorphic surfaces. But since you folks are watching me through YouTube, instead I'll do the demonstration myself, right? That we can sort of see the same picture happening, for example, on this waffly surface that we saw happening on the real line, or the real plane, sorry. As we delete those sort of larger and larger pieces, we still get that single connected component. And so it turns out that this waffle surface has just a single end, which is accumulated by genus, and so we can see that it's actually the same as a Loch Ness Monster. And in the same way, we can see on this sort of waffle with a sort of ladder glued on, that we have sort of this one single end here, just like our waffle has one single end. And then up here, we have sort of the same behavior that we saw on the real line, whereas we sort of chop out bigger and bigger pieces, we still get these sort of two directions, these two ends. And so this surface is actually homeomorphic to our Eiffel Tower. Okay. So we've talked a little bit about surfaces of infinite type. We've talked about their classification theorem. What about the mapping class group? Well, it turns out we still have a mapping class group for infinite type surfaces, and it's defined in the exact same way as the group of orientation preserving homeomorphisms of S up to homotopy. And so sort of a natural question, at least given what we've discussed so far, is whether or not there's a Nielsen-Thurston type classification of the mapping class group for infinite type surfaces. And it turns out we do not have such a classification at this point. Okay? And it's not even exactly clear what that classification would look like, because the behavior that we can see in this sort of infinite type world is much more varied than what we see in the finite type world. And so what I want to do I'm sort of building up to do this in part 2 of this talk, is to describe some possible analogs of pseudo-inosovs in the infinite type setting. Okay? And in order to do that, I'm going to introduce some ways that we can pass from this sort of surface world that we've been in so far to the world of three manifolds. Okay, so that brings us sort of to the next piece of this talk, which is surfaces to three manifolds. And so I really want to sort of make two connections. I want to make a connection with regards to building three manifolds from surfaces, and then also finding surfaces in three manifolds. And with both of these, I really have a much more specific thing in mind. So building three manifolds from surfaces, there's many ways to do this, but I really want to just focus on one, which is the mapping torus construction. Okay, so I'll talk a little bit about this. And then finding surfaces in three manifolds, again, there's many ways to do this, but I just want to talk about sort of one thing in particular, which is to just touch on this idea of having foliations of three manifolds. Right, so we can sort of decompose our three manifolds into collections of disjoint surfaces, in the same way that we could decompose our surfaces into sort of disjoint collections of geodesics. So the mapping torus construction, we'll start with that. So given a homeomorphism F from a surface to itself, I want to build a three manifold. And the way that I'm going to build this three manifold is sort of analogous to the way that I can use a circle to build a torus. Hence this sort of torus here in the name. Okay, so I'm going to start with a circle, right? So just to review sort of what we do to build a torus out of a circle, and then sort of leverage that into this bigger construction, right? We can take a circle and cross it with an interval. Right, so here's my S1 cross 0, 1. That just gives us a nice cylinder, right, or annulus. And then I can sort of glue up those boundary circles of my cylinder to give me a torus. Right, and so I'm going to do the exact same thing now, but instead I'm going to start with a surface. So in my picture, I've chosen a genus 2 surface. And I'm going to cross it with an interval to give me sort of this now sort of cylinderish type thing. You could also think of sort of taking your genus 2 surface and just sort of thickening up the wall of it, right? So instead of having sort of like that paper thin, sort of one-dimensional thickness, instead have a sort of like an inch there. So thicken it up. And then I'm going to glue, right? Just like here, I glued my circles to each other. I'm now going to sort of glue these boundary surfaces to each other. And the glue here that I'm going to use is this original homeomorphism that I started out with, right? Because this gives me a map of my surface to itself. And so I'll glue up by F, and that's what gives me my closed three manifold, right? So here I sort of see my mapping torus. I've drawn it a little bit suggestively. Okay, so this is sort of an important thing, and we'll touch back on this a bit more in part 2 of our talk. Also, it'll come up again in just a sec. Okay. So let's move on to the next piece of this sort of surfaces and three manifolds connection, which is surfaces foliating three manifolds. Okay, so I mentioned before, right, that what does it mean for a surface to foliate a three-manifold? We can really think of the sort of surface as sort of filling up our three-manifold. Sort of giving this, like, filling up of it, okay? And one way to sort of think of this as a nice example is to think of what it looks like to have a three-manifold, which is fibered over this circle. Okay. For example, if nothing is springing to mind, we actually just saw a picture of a three-manifold fibered over the circle, right? A mapping tori. And in a three-manifold that's fibered over the circle, well, the fiber is just a surface. And that surface foliates the three-manifold. Okay. So this is nice. That sort of gives us a concrete example to think of. And it turns out that these infinite type surfaces that we've seen actually arise naturally as the leaves of something called a depth 1 foliation of a three-manifold. So here a depth 1 foliation is a foliation in which any of the non-compact leaves of my fibration all accumulate onto my compact leaves. So you can think of it like if I see any infinite type surfaces in my foliation, they're sort of all accumulating onto finite type surfaces. And it turns out that these foliations generalize fibrations And what do I mean by that they generalize fibrations? Well, they're actually fibered in the complement of the compact leaves. Okay, so that's pretty handy. Okay, so these compact leaves, these are the finite genus leaves. And moreover, we know something about what the monogamy of that fibration looks like. So the monogamy of this fibration, this is sort of bringing us to the last piece of this talk, is in fact an n-periodic homeomorphism. Okay, so here we sort of are coming to the last piece, this idea of these n-periodic homeomorphisms. Okay, so let's go ahead and give an example to start off with. So first I've drawn an example that's just happening on this familiar ladder surface, right? This infinite genus surface with two ends accumulated by genus. And we can think of a homeomorphism of this surface called a handle shift. Where we sort of just take each handle. Maybe I can sort of redraw these a little bit more clearly so that they sort of look like handles if I sort of pull them up out of the surface like this. Okay, and we can think of these handles as sort of living on this infinite strip. Okay, so like here's my boundary of my strip. And my handle shift is going to be exactly just sort of taking these handles and moving each one over to the right. But I want to taper to the identity on sort of each of those arcs. Okay, and so this is going to sort of give me a action where I'm sort of I'm sort of moving everything over to the right, and I'm sort of shifting everything away from the left. Okay. Another sort of similar example, sort of putting these handle strips together. I could sort of lay them both down in my tripod surface, or my Eiffel Tower surface, and sort of think of shifting them again, sort of out of this end and into this, out of this end and into this. This is another example of an n-periodic homeomorphism. And then finally, I have as this sort of final example, this example which is coming from a paper, I'll just go ahead and write their names here, of Cantwell and Conlin. Okay, so this gives me sort of this shifting behavior happening here, and then sort of shifting out and happening here. Okay, so these are all examples of n-periodic homeomorphisms. And so I want to sort of now make this sort of notion where we have sort of this, again, sort of this repelling and attracting behavior into something a little bit more precise. But first I'll just sort of state it in a very hand-wavy way, which I'll just say that an n-periodic homeomorphism of S is a homeomorphism F of S, which satisfies the following, that each end of my surface S is either attracting or repelling under the action of F. Okay, so that's sort of what I'm seeing here, right? Like for example, on this surface, we have a repelling end, and then an attracting end and an attracting end. For example, if I had instead just put down sort of a single handle shift like this, that was just shifting to the right, then, and I didn't do anything on this side, then this would not be an n-periodic homeomorphism, right? Because these ends over here would be neither attracting or repelling. Okay, so it's important that I have this sort of for each end. So to make that just a little bit more precise, I can write down the following definition, which just asks that sort of you have for each end of your surface a neighborhood that builds yourself a neighborhood basis of your end under either forward or backward iteration of your map. Okay, so this is sort of what's happening here and here. This is, of course, a good bit more technical than what I stated last time, but again, it's just describing this attracting and repelling behavior. Okay, so I think we're going to pause there. Thank you so much for your attention. I hope you'll tune in to part 2 of my talk to hear more about n-periodic homeomorphisms and the way that we can relate them to the volumes of certain mapping tori.